Hello, everyone. Thank you so much for your time and attention. My name is Jeremy McCaslin. I'm Director of Fluids Product Management here at Ansys, and I'm very excited to talk to you guys today about one of our most exciting projects that we're working on, which is a GPU solver that's exposed in a couple of our applications. And today we're going to be talking about that in the context of Fluent. So before I dive into the details, I want to try to motivate this for you a little bit. Um, I believe that digital transformation really does require a step change in simulation capacity. So our customers, they really rely on and they need simulation to understand and to test how their ideas will perform against millions of variables, right? They want to be able to create digital twins that perfectly mirror physical assets, right? And that's going to require a huge number of simulations, ever increasing model size and complexity, and what that's going to amount to is generating unprecedented amounts of data. And we really need to drastically increase simulation throughput. And we have to do that without compromising accuracy. So it is a very tall order. We want to be able to do all of that while maintaining the gold standard accuracy that is Fluent, right? So let's take a step back, look at the past half century of CPU computing trend, right? And in this chart, a fairly well-known chart, you're looking at number of transistors on a chip, single core performance, clock speed, power consumption of the CPU. So around 2004, you can see a little bit of a step change in some of these trends. And the one I really want to draw your attention to is the one in black. That's the number of logical cores, and that starts to increase in the early to mid 2000s, right? And and that's when the era of parallel computing begins. And so if we look at Fluent's performance on a single node, so this chart is showing you single node performance of Fluent starting in 2008 is the initial point there. That's the baseline with a solver rating, let's call it, or performance throughput of 1. Um, and going through many, many years, if we look at almost about 15 years of data, what we see is that the single node performance of Fluent in the past 15 years has increased by over a factor of 90, right? So we have about 91x single node performance improvement in 15 years, which is pretty amazing, right? Pretty astounding. To give you, I give you that as context because if we introduce GPU computing, these incredibly powerful parallel devices, they have much more ALUs than CPUs, lower energy to execute instructions, higher bandwidth memories. All that translates to faster turnaround times, lower energy consumption, lower electric power bill, right? And ultimately cost savings for the customer. If we compare that single node performance back to 2008, instead of 91x that we're getting in the CPU context, we're getting a factor of well over 600, right? So that gives you an idea of the type of step change that we're talking about in terms of simulation throughput that GPUs enable. So that's why we're so excited about this, right? And if we look at a more concrete example, so in this image, we're looking at about a quarter of a billion cell mesh. And if we consider the performance we get on 176 cores for that, that's our baseline performance of 1. If we were to run this on 8 A100 GPUs, we get over a 23x speed up. If we run it on 32 GPUs, which is the bar on the far right, we get almost a 70x speed up. Right? So this is the type of performance improvement that we're providing to customers. That that performance throughput, you can view it as cost savings as well. So this was a benchmark that was done by a partner of ours on the cloud, and um, on that given day, you would pay a certain cost for a node, and on that node, you could use the 16 CPUs or the GPU on that. And so you'd pay the same amount, and you would get the same result on the left for the smaller mesh, about 50 million cells, about 24x um, cost effectiveness. On the right, same model but larger mesh, comes out to be almost a 40x improvement in cost effectiveness. So um, performance throughput, cost savings, right? That's what we're talking about in the context of the solver. And I was fortunate enough to go to NVIDIA GTC conference last month up in San Jose, California, and we're able to. A big part of why we're able to provide this game-changing tool to our customers is because of our strong strategic partnership with NVIDIA. And here you can see Jensen Huang, NVIDIA CTO, talking about the importance of Ansys as a partner to NVIDIA. And because of all this, we're able to provide to customers that value that we're talking about. So this is we were really excited to see Leonardo be productive with this new tool. So for this particular model, they were looking at aerodynamic loading on a tilt rotor machine aircraft that they're creating, and with the native Fluent GPU solver, they were able to run models 2.6 times faster with a third of the hardware resources. And so we want to be able to enable this type of benefit for all of our customers across the board. So for the remainder of the talk, I want to get into some of the 24R1 features that came out with our last release, which was back in January. We'll talk about some of the validations that go with the current release state of the code, and then we'll take a sneak peek into what's ahead. So let's move on to the 24R1 features. So the coupled solver is something that we're now providing. This is really important for a lot of our customers that are using Fluent as a workhorse for steady state simulations, right? So for under relaxation, that now supports Courant number. With the 24R1 release, the pseudo transient under relaxation was a beta capability, but we're very excited to be able to provide the coupled solver along with the GPU native GPU offering in Fluent. We have support for non-conformal interfaces and sliding mesh. So this allows you to do simulations that have rotating wheels, do full wheel turbo machinery, lots of different mixing applications like you see in the case on the bottom left. And then for external aerodynamics, if you're looking at cars, the rotating wheels is an important aspect that we can now cover with the GPU solver. Moving on to chemistry, we have both direct source, detailed chemistry, and the stiff chemistry solver now on GPU. Some very more canonical validation cases are on the right. You can see CPU and GPU results are indistinguishable from one another. Roughly 2.5 million cell premix ignition case, we see very similar qualitative results between CPU and GPU, CPU on the left, GPU on the right. And then if we look more quantitatively in the charts on the right, you can see the results are indistinguishable from one. Now looking at the Sandia Flame D case, really the same message. We see indistinguishable results between CPU and GPU. And I think one thing worth calling out, the box on the bottom right, one GPU in this case gave the same result as 32 CPU cores, but it did so 12 times faster. We now have support for the sponge layer in the GPU solver. So this will be an important aspect to modeling acoustic simulations with the GPU. And the animations, you can see CPU on the top, GPU on the bottom, and with the sponge layer on the right versus without it on the left. And you can see the sponge layer is doing its job of damping the acoustic reflections at the exit boundary. We also have beta support for UDFs. And this is really important because a lot of our customers rely on the customizability of Fluent. And so you can see here, these are Python enabled. So you can use simple Python syntax to write the UDFs in Fluent. So obviously we have lots of different macros that the UDF, the very powerful UDF capability of Fluent includes. So we will be migrating those capabilities to this new Python-based UDF framework for the GPU solver incrementally over time. We have, within the 24R1 release, we have beta support for Lagrangian particles as well. So this is an important aspect to lots of different types of models where you want to combine Lagrangian particle tracking with the finite volume method. And so in this particular example, this is about a 7 million cell lid-driven cavity example. And we saw the DPM calculation on one GPU ran about 18 times faster than 100 CPU. So right now we just have support for massless and inert particles and one and two-way fluid flow coupling. So we'll see in a later slide that the physics will be added to the DPM model. We also have beta support for both the discrete ordinates radiation model as well as the surface-to-surface radiation model. Let's take a look at a couple validations that go along with those features that came in the 24R1 release. So here we're looking at automotive external aerodynamics. This is a well-known benchmark, industry benchmark called the drive air model. This was presented at the Auto CFD workshops 3 and 4. So in this case, we're looking at, I believe this was a 500 million cell case, and we are looking at the drag coefficient on the car, both with and without this wheel deflector that you can see in that kind of teal color. And we were able to capture the impact of the wheel deflector on the drag coefficient, CFD versus experiment. That error in the difference, we were able to capture that well within 5%. In this example, we're looking at more of an aerospace related application. So this is the Onera M6 transonic wing, and we're looking at the equation of state here is ideal gas, and you can see in the contour plots on the bottom left, very good qualitative comparison between CPU and GPU. And then if we look at the pressure coefficient with first order density, we have really good agreement between CPU and GPU, pretty much indistinguishable, both agreeing reasonably well with experimental data. And then the chart on the far right, you can see that if we go from first order to second order density formulation, we see some improvement in the ability to recover the experimental trend. Here we're looking at the DLR combustor. So this is a reacting flow example. And so here we are, if you look in the top right, you'll see qualitative comparisons between the instantaneous result on the top and the time average result on the bottom. The CPU result is on the left and the GPU result is on the right. You can see really no noticeable differences there. If we take a more quantitative look and look at the species mass fractions at different cross sections in the domain, we have CPU and GPU in the black and red really close to one another at all locations, at all cross section locations. And in any case, I would certainly argue that the difference between the CPU and GPU results is well within the difference of the experimental data itself. This is another generic combustor benchmark. This was about a 12 million, polyhedral cell case. And here we're looking CPU, GPU qualitatively, the comparisons look really good. I'm kind of in the middle there. And then if we take a more quantitative look, we can see that the average quantities at the outlet, if we take the average species mass fraction differences at the outlet, it's near zero difference, and the maximum at the outlet is well within 3% between CPU and GPU. This case is showing some single phase multi-species cases that we've run. So we, as I mentioned before, we have sliding mesh and non-conformal interface. So we are working towards multi-phase mixing, and we'll talk more about that in a couple slides. But right now, we see good results in the context of single phase multi-species mixing. So let's take a little bit of a sneak preview of what's to come. So one thing I want to mention is that while adding physics to the new physics models and new features to the solver, we're also continually improving things like communication efficiency, right? And what this chart is showing you is that at 24R2, we have some really good optimizations in communication coming. And so at 24R1, we see that scaling was leveling off at around 10 million cells per GPU. So if you're looking at fairly small cases, like in this example, 2 million cell case, then we see the GPU solver isn't really scaling beyond 2 or more GPUs. At 24R1, with these communication optimizations, we're seeing performance gains in even below 1 million cells per GPU. So that's a significant, um, let's say, core functionality improvement that'll be coming at R2 that will benefit all users across the board, regardless of the physics that they're using. While I've stressed the partnership with NVIDIA, and that has been the initial hardware that we are supporting with the solver, we do have beta support in the 24R1 release for AMD GPUs. And here you can see a couple different benchmarks. Um, in the example on the top, we had 140 million cell open wheel F1 car, and that was running off on two GPUs, two MI250s. We saw performance that was about 16 times faster than 128 CPU cores. On the bottom, um, that same drive error model that we looked at earlier, but in this case, 50 million cells, we saw 8 GPUs performing about 20 times faster than 128 CPUs with 83% parallel efficiency. So very excited to be able to provide um, multiple platform coverage for this solver. So those are both, more, let's say, underpinning the physics that we add, right? That will apply across the board. In terms of the full richness of Fluent and getting that on the GPU, that is the ultimate goal. Obviously, like we said at the very beginning, we want to provide the breadth of physics and the accuracy of Fluent to our customer base. But it's a major task to be able to get these things into the GPU context without hindering performance, right? Without compromising any of the performance that makes us want to go to GPU to begin with. So we have a long, dedicated development strategy, right? Well, when I say long, really not long, but going back to 22R1, we had the initial beta release of the tool, and so we had two beta releases, and then 23R1 is when we had our first full release of the solver. And really, there it was about getting the core ingredients, the core DNA of Fluent, the general purpose, unstructured finite volume approach that allows this to be so broadly applicable into the GPU context. And now that we have all that there and validated, we're starting to add some of the more advanced physics. Which we saw a little bit of, things like coupled solver, um, and getting some of the chemistry there. So 24R1 is going to be, sorry, 2024 is a very exciting year as we start to make progress on the more, let's say, high-end advanced physics use cases in the GPU. So looking at 24R2 and beyond, we are seeking to add advanced combustion modeling capabilities there, including FGM, or flamelet generated manifold. As you saw, we have the inert DPM particles there, so we want to add mass transfer to those. We're working on the volume of fluid, or VOF multi-phase model, some more aeroacoustics capabilities coming, and then we'll be continually enhancing and extending the things that you can monitor, customization, like I said, UDFs will be incrementally fleshed out, release to release, improving numerics and post-processing, right? Like all of the user things that allow you to interact with the solver, those things need to be done carefully because we cannot compromise performance as we add those things to the framework, right? So here's a sneak peek of the GPU-based VOF method. So first and foremost, just take a look at the simple 2D dam break. That was really the very first thing that we saw with GPU VOF that got us excited. You know, the results all the way down to these little ligaments that start to break off. It looks, really no different between CPU, GPU. If you take that to a little bit more complexity and do it in 3D, which is the animation on the bottom, um, you'll see that one single A100 was roughly equivalent to about 3.5 CPU nodes for that case, which came out to be about almost 450 CPU core equivalency. In the case on the left, we have a cooling jacket filling and deaeration application. So you can see we're starting to bring the VOF capability in the GPU a bit more industrial strength, right? So in this next slide, what we're looking at This is courtesy of Lewis Clark from Leap. Um, he was doing some early testing of GPU, or sorry, of VOF on the GPU, and here we have this marine application where you can see the CPU and GPU results side by side are really very much indistinguishable from one another, and the total drag on that ship um, is a little more than 1% difference between CPU on the left and GPU on the right. So we're very excited about how things are coming along with VOF. So in conclusion, um, we're really excited to offer to the customer base this unique tool from Ansys. Um, you know, GPUs are becoming more and more commonplace in the CFD community. They've been around for a while, but most GPU-based codes that you see are certainly less generalizable than what we're talking about with Fluent. A lot of them are lattice Boltzmann or SPH-based codes. Um, a general purpose Navier-Stokes solver like this, from steady state to RANDs, we really do believe it and see it as one of a kind in the marketplace. So we've enabled you to migrate your Fluent workflows to the GPU with the flip of a switch. It's available to you at the CFD Enterprise license level. It runs out of the box. It doesn't require HPC to run on quite a few different types of cards. If you want to run on multiple cards or some of the higher grade server cards, then you will have to use HPC to do that, but it's compatible with your Ansys HPC with packs and workgroups. And there are multi-GPU cloud configurations available. Just to wrap up, let's talk about how you can stay connected and informed. So we have a series of white papers that you can access to read about some of the core verification and validation that's done with this solver. Um, and I wanted to point out that we have a second white paper that came out recently, and that's available. And so you can just Google search for that or reach out, and we can provide both of the white papers and all the blogs to you. And then lastly, please do follow us on LinkedIn. Post a lot of news about GPU, things that are coming there. So that's a great way to stay connected and informed as well. So with that, I'll thank you again for your time. And yeah.